Just saying,
hopefully I'll be hitting my head soon. I really gotta No, 6 foot 7. It's easier to say 6 foot 7.
6'5", 6'6".
It's after you defend your, whatever your...
You know what it is? It's the guys with the long legs. Long legs. They just go on. My father's not tall. My 5'10" or something. But my grandfather, they used to call him Big Red. He lived most of his life in Ontario. So he must have been up to 6 foot.
You've done everything except you haven't done it.
Because from that side.
That's how it
And I just Mandarin, just anything I read,
So good afternoon, everybody. Welcome to the last External New Frontiers seminar series. Today we're very fortunate enough to have Professor Scott Sheridan from the Kent State University in the Department of Geography, who will be presenting his research. Dr. Sheridan has completed his Bachelor and Master's of Science in Meteorology, followed by a doctoral degree in Climatology. And on today, he'll be presenting some of his findings on heat mortality related problems in response to the climate change in California. So let's give a warm welcome to Dr. Scott Sheridan.
Thank you. I assume you guys can hear me pretty well without me standing in front of the microphone? Okay. I tend to walk when I talk, so it's hard to keep me tethered. I'm honored to be up here today. I've had a great time here so far. Campus is really nice. It's amazing, you know, coming up from the U.S. to see campuses that are growing as rapidly as this one, that you have temporary housing for departments. It's probably not much fun if you're in one of those, but the fact that signals growth is actually pretty nice. So I'm here today to talk about a project that I've worked on for a couple of years. It largely wrapped up a couple of years ago, although we've kind of been doing a few things since and been moving on. But you know, I was asked to give a talk. I have a few different research interests. You know, I'm interested in synoptic climatology. I know some of you have already talked about with it, so you guys share that interest. I also have the interest in climate and health outcomes, and I also study climate change. And so, you know, you kind of look at all these things together, there's not that much that can actually tie everything together. But this project I worked on for the California Air Resources Board for a couple of years is one such project. And so this is actually the results from a 2.5-year funded project I worked on for the state, which had the goal as what you see up here in the title, looking at the projected changes in vulnerability in California in terms of human health outcomes to heat events as the climate changes. And so one thing which I do want to stress, one thing that I added, because from when I was originally thinking about this project, is the word uncertainty. That wasn't something that I started pitching to start with, but the whole concept of how we code uncertainty into any research projects we do regarding climate change has been something that has always fascinated me. But this project, which I'll show you by the end of this talk, you'll see why I'm even more interested in it with what we came up with. So since it's a long project, there are going to be a few areas that I'm going to have to skip over a little bit. You know, I don't want to eat up all of your Friday and into your Saturday. So, you know, if I hit something that sounds really interesting, but then I'm on the next slide in 20 seconds, I'll be around later, and I'm happy to answer any questions related to anything that strikes your fancy. So, a little bit of just briefly, the mission that we had with our project here is what you see here. This was the concept. To look at robust estimates of changes in oppressive weather conditions and heat-related mortality through the 2090s for 9 urban regions in California. And so the colored boxes, or the colored counties that you see on the map of California there. That's basically what I'm referring to when I'm talking about California. You know, it's only roughly a third of the area of the state, but basically it's around 80 to 85% of the population of the state. So they weren't interested in rural impacts, and so we didn't cover that. So now the idea that I took with this, which is fairly unique, is when we kind of look at the future, we try to look at weather circulation or weather situations. My main research framework has always been to use a synoptic climatological approach. And I know a number of you are familiar with it, but for those of you that aren't familiar with it, the main idea behind the synoptic climatological approach is that you take a suite of weather conditions that occur either over space or over time, and you categorize those into certain patterns or types, or air masses or circulation patterns. There's a bunch of different names depending upon what you're doing, and I'll come back to that. But the main idea is to try to gather similar situations. And so this was the way I wanted to approach this. You know what a heat wave looks like over California. California is a very diverse state climatologically. If any of you have been to the Bay Area, you know that if you go just a couple of blocks, the temperature might change by several degrees just by the sea breeze. And so we wanted to look at larger scale situations. I've also done a lot of work on heat warning systems, including one for the city of Toronto. And those heat warning systems are based on the same concept of synoptic climatology, that gathering everything together and making a holistic assessment. So we had a basis for using this. And then the other thing is that, in a couple of initial projects I worked on, climate downscaling didn't really perform very well. We look at climate change impacts. We know climate models project global circulation. How you then project that down to the local area has always been tricky. And especially given the climate of California and its diversity, it's very difficult to get very precise, accurate, downscale data for a place where the climate changes dramatically in just a few kilometers. And so the idea was, forget that. Don't attempt to try to categorize things that small. Instead, you use upper level patterns. And this is an upper level temperature pattern I'm just putting up here as an example. You use those to try to derive what you believe the synoptic situation is at the surface. So rather than try to prescribe exact numbers, you try to understand situations. So it's a very different framework. And it's also very difficult to deal with statistically, in terms of how you make assessments. Now the other thing that comes up is, when we look at the future, what do we have to account for? We know that we're used to all the greenhouse gas emission scenarios, the SRES scenarios or RCPs, that tell us greenhouse gases might go way up, they might go down, and we know what our impact on carbon emissions and so on might have on the climate. So that's one level of uncertainty. We also have to deal with model bias. Some models are just more gun-shy than others, and so that's that. One thing a lot of climate studies don't actually account for is the fact that populations are going to change. Not only are there going to be larger populations in a number of places, but we're also going to collectively get older. We know that older people are much more vulnerable to the heat than younger people. And so if we're trying to get a robust understanding of the future, we have to understand different population scenarios. What is 2090 California going to be like? It's not going to be the same people that are there today. And then lastly, one thing I'll come back to a little bit at the end is the whole idea of acclimatization or adaptation. We know, there's a ton of literature out there that says that people in warmer cities can tolerate temperatures, and their built environment is generally structured to help them deal with higher temperatures than people in colder cities. It's still very difficult to understand what happens if you take a city and then you change the climate of the city. Do the people acclimatize? Do they get used to the warmer temperatures? Even though the built environment around them is the same. That's something that we're just now trying to deal with, and I do a little bit of that here that I'll show you at the end, but there's, it's still a very open question. So there's basically going to be 3 parts to my talk, or more or less 2.5, because part number 2 is just going to be one quick slide. But the main guts of what I want to talk about is I used synoptic methods to try to derive what weather is going to be like in the future. So that's stage 1. Stage 3 is, what does that mean for the population? And so the link there is that in stage 2, we had to see how people responded to the weather in the present day. And that has a robust set of literature. I'll show you a very little bit about that, but that's not the most interesting part of this, because there's been a lot of other research on that front. 1 and 3, I think, are what's most unique here. So we'll start out with future patterns. And I know a few of you know this scheme pretty well. The spatial synoptic classification is something that fell out of my dissertation. Eventually I'll get to the point where I'll stop putting the year in parentheses, but it's not that far ago, so we'll keep going with it. It involves a classification of weather types, or of weather situations at a given location into one of several different types. There's 7 primary categories that you see up there. And then there's a couple subset categories that I'm not really going to talk about much today. The 2 that I want to focus your attention on, just in case you don't want to learn a whole bunch of new acronyms on a Friday afternoon, are DT and MT, the 2 tropical types. Basically just think really hot and dry weather and really hot and humid weather. We're talking about heat-related mortality. These are obviously going to be the ones that are going to be of interest to us. And so what the SSE does is it takes all of these observations from the surface and creates a categorization. So now if we want to understand how things are going to change in the future, computer models don't generate new SSE types. If you try to get the raw data that go into an SSE type, some downscaling just really doesn't do a very good job. I was mentioning at lunch that our initial foray into trying to project downscaled variables for Los Angeles was a disaster, because it was basically picking up on the heat of the desert, but the availability of moisture right offshore to create dew points of over 38 degrees C, which is obviously not very feasible. And so, trying to derive the overall weather situation versus trying to derive all these individual parameters is a very different approach. So how do we get there? Well, one thing that we know is that upper atmospheric patterns do have a connection with surface weather. There's a very clear understanding that if you have a ridge, or you have a trough, or you have a certain thermal pattern, that's associated with a certain type of surface condition. And so we have historical patterns. Climate models also produce them, and they generally produce them pretty well. It's one of the broad patterns. They generally have a good handle. For the SSE type, we of course have the past, but the big question mark there: how do we get the future? And so there's a few different stages here. First, just a little bit about the weather data sets. If you're familiar with atmospheric data, a lot of this will be familiar to you. We're looking at atmospheric circulations at 2 levels, and then lower tropospheric temperature, 850 millibars. We use reanalysis data, the nice gridded data from NCEP NCAR that basically is kind of a reconstruction of the past. And then we use 2 global climate models. These ones are now a little bit archaic. There's newer models of them, but given the long time it takes to get projects up and running, these were state of the art when we started. So, and if you're not familiar, we use several different IPCC scenarios. The idea of changes in carbon emissions moving forward. And so there's 3 different scenarios that I'll show you. One is the most aggressive of all of them, the A1FI. FI stands for fossil fuel intensive. And then you have an intermediate scenario, then B1 is kind of more the environmentally friendly scenario. So as far as uncertainty goes, we're looking at an entire range in terms of a lot of carbon emitted to a relatively modest amount of carbon being emitted. My PhD student Cameron and I spent a couple of years working on a project to try to figure out how to actually derive future weather types. And this is the part that I'm going to skip over a little bit, largely because it's not astoundingly thrilling to talk about. The fundamental flow chart is what you see there on the right. It's called a six-step method. It basically involves a number of different stages where you train different data sets to try to predict surface weather character. And so what we did was we took, we took synoptic categorizations for each of the three levels of the atmosphere I showed you. And we used those to try to understand the relationship between them and surface SSE type. You know, there is a connection. We then repeated that, seeing how well GCMs could do it. And then once we were confident of that, then we dumped in the future data to see how well GCMs would change things moving forward. And so we did our best to do what you see there on the bottom, which is that future patterns are derived to resemble the historical patterns as closely as possible. One, of course, offshoot of this is that with climate change, sometimes you get new patterns or new circulations that don't exist in history. And so that's one kind of inherent concern with any sort of project of this sort, and I'll talk a little bit more about that somewhere later on. Anyway, the guts of this are in a paper that Cameron and I published in the International Journal of Climatology a few years ago. This was actually the basis for his thesis work, where he was doing the same thing with tornadoes in North America, which it actually also worked very well for. So a little bit about what we see, you know, and don't overwhelm you guys with a bunch of stuff because I'm talking about this, you know, more conceptually. But you see two temperature patterns that are shown here. This is kind of the region we used for California. We have to go into the Great Basin a little bit because Santa Ana winds that bring really warm air to the coast. You need to resolve the patterns that are further east of the state. And so we see two temperature patterns that are kind of more hot and hotter, if you want to give them basic descriptors. And these are the ones that actually most likely lead to a weather event that would be deadly for people at the surface. And you can see it's a little bit small, but you see March through November, the warm season. You can see they basically peak in the middle of summer, which makes sense. You can also see the red is the actual, and the blue is what the model reproduced historically. And you notice that the patterns are actually quite similar. Meaning the models successfully reproduced these patterns with the frequency you would expect. So in other words, that gives us confidence that the model adequately has a handle on the realm of variability of climate circulation. Now we did this with all 30 patterns. You know, I'm only showing you two here to make a concept, but we basically have the exact same thing with all 10 temperature patterns and then all 20 upper level circulation patterns. And so we can look at how those change. Now what's interesting about looking at this climatologically is that, you know, some of the changes are fairly logical, but they're not all exactly the way that you think. And so you see pattern 8 and pattern 10 here again. And you see the yellow is history, and then the red, green, and blue are different future scenarios under different greenhouse gas circulation. And what you see if you look is you notice that there are some patterns, like pattern 8 over here, where you see the patterns become more common in the future. What's interesting is you notice a large-scale seasonality shift here, where you notice that pattern 8 starts to become a lot more common in the spring, but then it entirely disappears in summer. It becomes actually less common moving forward. Whereas you look at pattern 10, and pattern 10 actually just becomes far more common throughout the entire year. So not everything ends up being, you know, very similar. It's not like all hot patterns become more common, all cold patterns become less common. Instead, when we look at this, we actually see seasonality changes. You know, and this, of course, is going to be critical. So then how do we get to surface weather conditions? You know, it's great to have upper atmospheric patterns, but if we're going to look at human health mortality outcomes, well, maybe we want to know what's going to happen at the surface. And so what we basically did was we took a lot of information out of the mapping that we did of the upper level patterns. And we used multinomial logistic regression, which basically feeds into it weather types. You're giving it multinomial, you're giving it a multiple number of discrete categories, each weather type. And then you're giving it all the other information. You're giving it the upper level patterns. You're giving it information like time of year, a lot of principal components that fall out of the analysis. And then it uses that information to predict what the SSC type will be like in the remainder of the data set. The GCMs actually do an excellent job reproducing SSC types. You know, this was kind of the big moment of truth. Is if the SSC, the synoptic categorization, is a little bit tough to get a handle on, a little bit tough to understand. Can a computer model adequately reproduce the number of times a certain weather type occurs? And it actually did an excellent job, except for polar types, which is a little bit weird. But polar types are very rare in California. And so and they usually have very strange signatures to them. And so it makes sense that they might not have a good handle on that. Also, since we were doing heat-related mortality, polar types weren't the thing we cared about. So I note that, but that really didn't have a huge impact on our results. So what do we see? So there's a couple of things here. One of the biggest struggles we had over the course of this project was we were producing astoundingly large volumes of data. And trying to figure out how to actually present this without overwhelming people was a little bit tough. And so we actually did, I think, successfully boil it down to a few graphics. So, let me explain this and hopefully it'll make a little bit of sense. We basically took California, we divided it up into 6 different SSC stations. And I meant to point that out on an earlier map that had them, and I forgot. But what you see is, if you look at going across the top, Sacramento, Fresno, Riverside. These are 3 inland stations moving from north to south. If you look at the bottom, Mountain View is the Bay Area, El Toro is Los Angeles, Miramar is San Diego. So north to south, but along the coast. All right, so if I had better artistic skills and I kind of turned it 90 degrees, you could almost see a California, where you go north to south inland, north to south on the coast. And so what we see here are projections, decade by decade, for the average number of times these 2 oppressive weather types occur moving forward. And we see different models. The one model, the CCSM, is a line. The CGCM, where I only had 2 snapshots or points. And then the different scenarios are the different shadings or different shapes to the dots. And so we see a few things. We see that if you look inland, you notice that especially in the desert south, the warm humid type just never becomes more common. The desert stays dry. But it gets much hotter and drier. You look towards the coast and you actually see that much more high humidity events actually become more common. And this is interesting because if you actually look at a few of California's heat waves over the last decade, one of the unusual aspects about them is that they've set a lot of records for really high overnight temperatures. And they've seen relatively high dew points as well, which means that what this is suggesting is that a lot of these events are going to change in character. So rather than being hot and dry, at least the way we're projecting it, there's going to be more hot and humid events that will take place. And so the spatial patterns do vary. The Bay Area here, you actually don't see a huge change, but you go down near San Diego, and you do. Similarly, if you look inland in Sacramento, you see the possibility for a lot more humid events than you do in the current day. So there's a lot of information here. The other thing that we see is fairly typical of most global warming, or excuse me, climate change projections, which is that right through the 2040s to 2050s, you notice the lines tend to be clustered, and then starting in the 2050s, they diverge. You know, and we can see a number of examples where with the B1 scenario, you see oppressive weather actually either flatlines or in some cases actually decreases towards the end of the century. Other times it goes up, but just at a slower pace. So far so good. You know, this model adequately reproduces weather conditions at the surface historically and projects feasible patterns moving forward. The seasonality can also be looked at. And again, a little bit of orientation here. We only looked at 9 months, so it's March through November. You know, California does get Santa Ana winds in the winter, but they, you know, it can get warm, but it tends not to be deadly. So we're kind of looking just at March through November. And if you look at this chart, you see the solid line represents the historical seasonality. So dry is obviously brown, and moist is green. And then the shaded area represents the GCM range across all the scenarios. To give us an idea of uncertainty. And so what we see is, if you look at the inland stations, you notice that you see the dry tropical becomes a lot more common. In some cases, it starts much earlier in the year. What we also see, though, is in Southern California, you notice that if you look at here, this is Los Angeles, and here, this is San Diego, presently, you actually don't have very many hot, humid heat events in the summer. But the climate models are projecting, at least with the way we've done it, that you're going to see the potential for a significant shift for there to be a lot of really hot, humid events, especially for some reason in the month of August. Probably due to water temperatures. So, you know, it's not just a matter of things happening more or things happening less, but when we combine things together this way, we actually see seasonal shifts. You know, again, inland it's not nearly as interesting of a change. Things just tend to become more common. But near the coast, where you have a lot more going on, you see a lot more things happening. The other thing I want to point out is that, especially if you look at the MT down here, these shaded areas are enormous, which is an indication that the models and the scenarios are just in very, a lot of disagreement. So how much of that is scenario related versus model related versus the way we're doing the modeling is a good question. So if you sum it up, you know, we like to, with the work that we do on heat impacts, we like to call the tropical days oppressive days or offensive days because they tend to have the most negative impact on human health. And so if you add up the number of oppressive weather days historically in California, you come up with the numbers that you see here. You look at the future scenarios and you see obviously things are invariably going to be higher, but the range is actually quite substantial too. And you notice that some places, you know, like Mountain View, which is in San Francisco, you see maybe a 20% increase to doubling. Other ones like Miramar, which is San Diego, you might be 3.5 times what you were before. So you know the differences actually vary a lot. We can also look at really long heat events. You know, these are the ones that tend to lead to the greatest death tolls, and I'll come back to that in the second half of the talk. They're relatively rare now, aside from the two inland cities of Riverside and Sacramento. But you see, they're projected to actually become far, far more common moving forward. This is the annual number of times 10 oppressive days occur in a row. The weird thing about this statistic is that eventually when you make things so hot, that number starts to go down because heat events start to merge to each other. So in other words, you know, if every day was offensive, you actually only have one heat wave. It just lasts 100 days. So you kind of have to take this number with a little bit of a grain of salt, realizing what it's actually telling you. All right, so I'll now turn to looking at the general impacts. And again, as I said, this second bullet is going to be very briefly discussed because this exists throughout literature. The idea is, to understand what's the relationship between weather and health, particularly with the concept of heat-related mortality. And so what we did was we ran a number, and this is going to be small deliberately, so I don't try to microanalyze it. I know myself. This is basically the set of results looking at the relationship in all 9 cities that we're looking at, 9 metro areas, between weather types and mortality. And now the only couple things I do want to point out from this graphic is that one thing which we also did was we broke this down by age. So we stratified things by age group. Under 65, 65 to 74, and 74 and older. And we did this because we know in the heat literature that as people get older, their vulnerability increases. But remember, we're also going to be bringing population change into account. And so we have to have an understanding about the weather-health relationship for people under 65 and then for people over 74 and the group in between to help us understand what demographic change says. So the way these are all done, a lot of this is basically more or less standard from the literature in terms of the way the standardizations were done, and I won't talk about that more than this. So we understand the weather-health relationship in the past. We have projections for weather types in the future. How do we marry those? How do we combine those so that we can understand where we're going in the future? So we have the relationships, of how deadly heat waves can be to people under 65, how deadly they can be to people 75 and older. The big thing now is, well, how many people are there going to be? And so the state of California, the Department of Finance, actually has population projections. They go out to 2100. I've never seen any other place have them, that far in advance, but it's interesting. And they do it by age group. So you can actually get it down to increments of 5-year increments. I only used the 3 breakdowns that I just showed you, but we have those. And they give you 3 different scenarios. The low population growth, 48 million, really only puts it a handful of percent ahead of where California is now. The mid-range growth, 85 million. The high growth is almost certainly implausible. It actually projects birth rates are going to start to go way back up in California, which seems really unlikely. But I wanted to frame it, and it's an official projection from them. Yields 148 million people living in the state by 2100. To show the relative importance of population change, I also ran this, keeping one other scenario, which is no growth, keeping the population exactly the same as it was in 2000. This is not feasible, but my point is to show what vulnerability is related to demographic change and what vulnerability is related to climate change. So in other words, if you could freeze the population in time but change the climate, what would you see? So again, we probably spent a lot more time than anything else struggling over how on earth we're going to make sense of over the seemingly millions of numbers that we produced here. There's a lot of axes of uncertainty here, and I'm just going to show you a couple of examples. If you look at short-term mortality over Los Angeles County in a given year, on average, around 165 people die on hot days, more so than would be expected. Now some of that is short-term displacement, and issue I'll come back to talking about at the end. But if you look just at short-term increase in mortality, that's the average. What you see here are the projections for the 2090s. I apologize that you can't read all that, but future heat-related mortality, annual mean, Los Angeles in the 2090s. For the different models and the different levels of growth. And one thing which stands out immediately is that you obviously do see variability from one model to the next, and you do see variability among the scenarios, but you notice that your bigger source of variability is actually if you go across the columns and not down the rows, which means the biggest form of variability is actually in what the population base we use is. If you just look at no growth model. So in other words, you pretend the population never changes. None of us want to get older. And if we do that, you see that the changes are roughly 3 to 4 times what they were historically. You take that implausible one, and again, I'm not saying this is realistic, and you end up with increases in mortality that are now higher than before you saw. The numbers here are key to where 1 represents average conditions historically. So in other words, this is how many times the historic value are we going to see heat vulnerability or heat mortality in the future. And so if you look across the 9 regions as a whole, what you see is projections, if you just look at climate change alone, of a doubling to 4-fold increase in heat vulnerability. You throw in demographics, and this is just the median population growth, and that increases to 9 to 17-fold. And there's a lot of variability from one place to another. The Bay Area is actually fairly resilient. Largely, well, for 2 reasons. One, the Bay Area isn't going to grow as much as the rest of the state. It's already pretty packed. And so the population projections there aren't that different in the past. But the climate is also not, it's also about the most benign climate you see in the state. And so we don't expect huge differences. When we go back to those weather types, you didn't see as huge of a change in the Bay Area as you did elsewhere. And so even in the median population growth, you see 3 to 4 times as many people being more vulnerable. You look at San Diego, and that number is 11 to 27. So obviously, just in the 700 kilometers between San Francisco and San Diego, we're talking about very different potential impacts with the way the climate is projected to be. So now back to my first point, or one of my first points. Adaptation or acclimatization. It seems logical that our relationship with the environment is going to change, in a number of different ways. But one of these is that we're going to deal with hot weather differently. And you can see a number of examples. You can look at, like after the heat wave in Europe in 2003, how many more places had air conditioning than before, because they suddenly experienced something which their normal built environment just couldn't come close to handling. You can look at places like Seattle, where a number of heat waves over the past several years, including an all-time record high temperature of 39 Celsius, I think 4 years ago, ended up leading to a big increase in air conditioning there, largely because they couldn't acclimatize. We would have to assume that more people will have air conditioning, for better or for worse. Obviously, there's environmental negatives to that, but in terms of adaptation, we have to assume this. There also is the potential for physiological adaptation. That we biologically adjust to warmer temperatures. The problem is that when you try to quantify these, it's tough. It's tough because we don't have very good statistical data on this. We haven't had enough of a trajectory of climate change and long-term data record for us to do the really detailed statistical analysis we would need to say, okay, people mortality was starting to go up at this temperature back then. Now it's a little bit warmer and it's this temperature. We really just can't. There are several studies that are doing this, but the results are not all that conclusive. There's also research that suggests that heat waves are worse than individual days. So in other words, 3 hot days in a row are deadlier than 3 individual hot days scattered about a month. And so, just to get an idea of approximate adaptation or acclimatization, I used 2 different approaches. One is called DIS2, Day in Sequence 2. It eliminates mortality on the first day of event. So in other words, people, mortality tends to go up as heat waves get worse. So let's just estimate that no one dies on the first day of a heat event anymore. Again, it's a crude approximation, but there you go. And then the second one only starts mortality on day 4. This is kind of a broader one. And we see both of these reduce heat mortality quite a bit, 20 to 40% and 40 to 70%. I don't remember if I put in a graphic or not. I did. Yeah, this varies a lot from one place to another. The mortality reduction is actually higher in places like San Francisco because, again, they don't have very many heat waves and they tend not to last very long. So people acclimatize, they can deal with it better. In Southern California, you typically don't see as much of a reduction. It's still decently high, but not as high because you tend to have more heat events. And I don't remember if I put the inland cities. No, I didn't. So, you know, again, I apologize for all the numbers, but, you know, I like to show the raw numbers just to give you an idea of the magnitude of the differences that we're looking at. So, summing it all up, this graphic is actually the final set of numbers I'll be showing you today. It basically kind of summarizes everything that you know, I've shown you to this point in terms of mortality. If you look across California as a whole, historically you see values, you know, roughly 500 people a year die in terms of short-term increases in mortality due to heat. You look at just climate changes, and you see that's going to double to quadruple. You throw in median population growth, and you see that those values then become much, much higher potentially, upwards to 4,000 to 9,000, or 3,000 to 7,000 if you add some form of acclimatization. And again, there's a lot of spatial variability, as I already kind of pointed out. So now, what does this all mean? You know, after producing tons and tons of numbers and tons of statistics, and you know, seeing how all this comes out, I want to come back to the concept of uncertainty that I started out with here. You know, there's all these different forms of uncertainty going in, and I really didn't have any clear idea of what was going to be the most uncertain aspect of what I was doing. You know, that's something that we have to acknowledge in any bit of research is, you know, the notion of what uncertainty is, what can you be less sure about. And so what I actually didn't expect was that the population scenario was actually going to be the most uncertain component of this, the biggest driver in the variability of one number to the next. Now some of this is a little bit loaded by the fact that that high-end one that's implausible is in these numbers. But even without that, you know, the notion that we don't really have a very good handle on how many people are going to be around in the future and how old they're going to be, along with a bunch of other factors involving wealth and so on, is actually a bigger amount, provides more uncertainty to our projections than greenhouse gas changes. The most environmentally friendly and the most environmentally unfriendly, if you want to call them that, scenarios were around 80% apart versus a 200% difference in population. We only had 2 models. You know, now it's a lot more in vogue to have far more models. And it's gotten easier to process them because a lot more model data is given out in standardized formats, so that you don't need to deal with them as much. But the 2 models we showed were slightly different, but 10% is minuscule compared to everything else. And then the last one is acclimatization. You know, I kind of just came with some crude ideas for this because it's very difficult to actually figure out what we're actually trying to say here. And that gave us roughly a 60% difference from none to the most extreme. So, 2 final slides of thoughts, and then I'm happy to take any questions. I didn't really show you much. This is contained in that little tiny chart I put up for a few seconds. The heat mortality relationship is most significant for those 75 and older. In California, it is rates are roughly 8 to 10 times what they are for the sub-65 population. You know, just vulnerability goes way up. Remembering that in demographic changes, this is the subset of the population that's going to grow fastest. So we already see this, you know, looming. Population growth increases vulnerability. It also increases our uncertainty. You know, one of the interesting things about a lot of climate change studies that look at future impacts on population is that the concept of an aging population is put in as an afterthought or just as a form of uncertainty. But there are projections out there. There's a number of studies that actually use it, but there's a lot more that don't. And so the notion of accounting for the fact that we're going to change as well, I think is critical. We do see changes, both oppressive days become more common. The inland becomes hotter and drier. The coast becomes hotter and more humid. We did see variability along the coast, so it wasn't kind of an easy way to summarize. We also see a lot more very long-term events. The GCMs actually were generally pretty good, at least with the two that we had. We see divergence after the 2040s, with vulnerability kind of peaking after the 2050s. Vulnerability only goes up in the more environmentally friendly scenarios after the 2050s because the population continues to get older, not because the climate is changing. And acclimatization is going to be a big deal, but again, probably one that's quite difficult to quantify. And so the very last thought is, I like to kind of end with this. This is actually not related to human health at all, but kind of related more to public health, which is the notion that when we look at climate change and its impacts, we always have to remember the perspective that there's a lot of things going on that actually don't have anything whatsoever to do with climate. And the graphic on the left shows the potential expansion of malaria. I don't remember into what decade, but you see Europe and parts of North America lighting up quite well. But then, of course, as a reminder, this is actually from the CDC. This is showing the outbreak of malaria through the United States. And I don't remember what year it was. I think it was in the teens, if I remember right. To show that malaria was endemic in the United States, or had epidemics in the United States, right up until the late 30s and early 40s, where the infrastructure to eradicate malaria was invested in. And so when we look forward, we have to kind of look at the idea that we do have a lot more capability for dealing with issues, but that has to be accounted for. All right, so I think that's it. So thank you, and I'm happy to answer any questions.
You got me thinking about all the confounding effects, of course, and population and economics. And some of the literature, I think, I'm not aware of literature well, but that they're trying to make correlations between GDP and temperature and those sort of conditions. This seems to be something new. We just have to start thinking about net out migration from areas that, at what point does a region's climate start to affect GDP and start to affect livability of the area? Is there anything like that in the literature? Like, I don't even know. Like, I know that people live in Arizona and it's supposed to be hot.
Yeah.
That sort of thing.
I mean, I've seen some studies on that. I mean, some of it tends to then creep towards environmental determinism, which I think that no one wants to go too far down that route. I mean, there are a number of studies that look at extreme event vulnerability and how populations adapt relative to their wealth. And you can actually see, there's some. If you kind of just look, say, within cities, there's actually some studies in Phoenix from Arizona State where they actually looked at vulnerability within different neighborhoods. And they correlated with income levels, where therefore you don't have other kind of larger scale factors at force, but it's more just kind of looking at that. And they do show much, a very strong correlation between wealth and vulnerability there. And ironically also heat island, because the richer houses can afford grass, which then mitigates the heat island, whereas the poor houses don't. And obviously Phoenix is just that's an anomaly unto itself, but nevertheless, it was interesting. So there is a lot of that. One of the things that makes it very difficult with a lot of this research is that getting data from the developing world to do detailed analysis can be pretty tough.
Yeah.
piece on demographics and climatization and adaptation to changing conditions. I'm wondering if there's another piece there, and maybe it's preconditioning. The city of Toronto, there are 47% of people who live in Toronto not only were not born in Toronto, but weren't born in Canada. And so we have a population here of a large portion of individuals that have actually come from another climate and live here. Our largest flux of immigrants at the moment is from the Philippines, which is a much warmer climate than Canada. So does that kind of changing demographic need to be factored in terms of understanding adaptation, or what appears to be adaptation but may actually be preconditioning? They're just waiting for the climate that they grew up with, for example.
Yeah. That's a really good question. I mean, one thing I'll say, I was hoping we would do some breakdown by race or ethnicity in California, because those California projections actually do have race and ethnicity. So we have a large Latino migration, but the problem is that the census and the death records actually did a really bad job of recording that for us historically. It's fine now, but we didn't have the period in the past, so we couldn't do that. I think that's a really good question, though. I know there are some studies that look at race differences in mortality. I'm not actually aware of anyone that looks at race or ethnicity differences and then related to where they're born versus where they're currently living. I mean, if anyone knows that, I'd really like to hear about that. I mean, the statistics on finding that might be tough. I mean, I know, again, I'm speaking from my U.S.-based perspective, but on the mortality data set that I have that I work with that forms the backbone of all this, if you're not born in the United States, you get code 99, which is other. Which so we're America, that's the way we are. So it doesn't help. But I mean, if you have databases on where people are from, that would be. I do have a colleague that's actually, and I guess it does relate to Canadians somewhat, is looking at trying to figure out snowbirds in Florida, and the fact how people that spend half their retired years in one climate then return to another climate, how do they deal with weather variability different than people that spend the entire year in one climate? And so I know someone that's looking at that, and that's the only complicating factor is that not all the snowbirds report both addresses, which makes it, and a lot of it's for tax reasons, which I understand, but it's not, we all know what snowbirds are, but when you look at the data, they're hard to pick out.
Yeah, and remember you mentioned what were they most interested in terms of, I imagine that they were interested in preventative measures or population education?
That's a good question. The California Resources Board is, they're kind of similar to our Environmental Protection Agency of sorts, but they also have a lot more kind of planning decision capabilities than a lot of other agencies at the state level. And so a lot of the original reason they wanted this was more so for kind of proof as to the need to mitigate greenhouse gas emissions. The way it just showing the vulnerability. Actually, what was interesting is they originally didn't particularly care about the population changes. That was something that I thought was really interesting, and so added into it, but it wasn't originally thought of. They were just more interested in showing that heat waves are going to clearly get worse. This is also right after this got funded right after one of their times when they had a huge energy shortage, which they occasionally do during the worst heat events, where the power grid just gets sucked dry more or less. So some of it was aimed at that too. But unfortunately, right when this was released, California had one of its biggest budget deficits, and so all future work of things related to this then went to their biggest problem, which was securing the energy grid. So it hasn't, it had legs that then just kind of, sorry.
When you're looking at heat-related illnesses, are you looking strictly at dehydration and heat stroke? Because there's also other things, particularly in California, between smog and wildfires, which are a pretty big issue. Have you looked at those, or?
There's one thing no, but one thing let me step back. One thing which I didn't mention is that when we look at vulnerability, we tend to look at vulnerability from all causes. So we look at mortality, how many people die in a given day. You know, so this is all causes. It's not just people that die of heat stroke or die of you know, something related to that. It's everything. And that's because a lot of research shows that mortality from a lot of different things, basically just about everything other than long-term illnesses, mortality goes up significantly on hot days. So the statistics I showed you were kind of a broad-based assumption. Now, your point, though, is a really good one, which is that, you know, pollution, either from wildfires or ozone, you know, can also be deadly. And you have, obviously, you know, relatively bad air for North America in a number of places in California, more recently, especially the Central Valley. So that certainly is a confounder. One of the toughest aspects is that pollution tends to be worse on the days that are also hot. And so I know there's some studies that have actually tried to figure out how you, and actually some, you know, even here in Toronto, that have tried to partition out heat mortality versus pollution mortality. You know, and the fact that in the summer they tend to be strong confounders of each other means you get very different results depending upon the statistics you use. So you are right with that. The one thing I will say, though, is that with our synoptic approach, you know, even though we don't look at pollution as a separate entity, you know, if you're looking at the overall atmospheric circulation, pollution levels are very nicely stratifiable by synoptic type. And so you can say that certain weather types have a much greater likelihood of high pollution, which also has that impact. So, you know, implicitly it's in here somewhere, but explicitly I can't tell you.
I was wondering whether the stations that you use for all the 9 cities, are they like close to within the proper city, or is it like a little bit further away? For example, for San Francisco, are you using like the airport, which is pretty like half an hour train away from train distance away from the actual city itself? Or because in Toronto, if you're using the Pearson airport data,
Yeah.
it is about 1 or 2 degrees higher than if you go to the city airport, which is where most of the people in the proper city itself.
That's actually a really good question. We spent a lot of time trying to deal with that. You know, and some of that, you know the SSC, so some of that is going to be, there has to be an SSC station there. And I made new ones for this, but you know, to create an SSC, you need to have a lot of overnight weather data, which is a big limiting factor, because a lot of airports before the automated era shut at night, which would mean you would not have that. So there needed to be appropriate weather data, but it also needed to be in the right climate type. And so, you know, one thing which, you know, I don't think I explicitly stated, but when I showed you these results here, you know, the top 3 probably all make sense to you as places you know or you've heard of. The bottom 3 probably just all sound really strange: Mountain View, El Toro, and Miramar. And those were all former military bases, some of which, Mountain View is now turned into a civilian air base. El Toro is closed, and Miramar is still a military base. But basically, those 3 are actually slightly inland by several miles. And part of it is because the climate right along the coast is really very chaotic. But the other thing which we tried to do is we picked the weather station that was closest to the centroid of the population that we were looking at. You know, obviously, if you're looking at a metro area, everyone's going to have a whole bunch of different experiences going on. But for the way we worked with this, we wanted it to be as close as it would be. So like San Francisco Airport is a bad example, would be a bad example to use because it is right on the water, it is off on one side, you know, whereas most of the population in the Broad Bay area experiences weather warmer than what the city of San Francisco experiences. And so that's why Mountain View, which is a little bit down closer to San Jose, we thought was a little bit more appropriate.
Then perhaps maybe you could use Oakland instead of to represent San Francisco because it's probably closer, right?
You know, there's something wrong with the Oakland data. Because we did actually look at, Oakland was the first one I thought of. I mean, Mountain View, I didn't even know what that was until I got desperate when there was nothing in the Bay Area that worked. But I want to say Oakland either didn't have a long enough record or they're missing nighttime data. I think there was something, I don't remember, but
Okay.
thanks. Yeah, it's a very good point, and I neglected to mention that in here, but that is very useful. I will also add, just along that line, is one new line of research. I haven't actually done much in this, but I've seen a lot of this over the last few years, is that there's a lot of researchers trying to correlate outdoor weather with indoor climate. You know, and you know, obviously all of this is a proxy. You know, if I'm going to die of heat, it's not because of what the temperature is outside, it's because of what the temperature is surrounding me. And so there's a lot of really interesting research trying to capture the hyper-local level, which is basically the you experience. You know, what are people experiencing in their homes and their bedrooms? And so I think it'll be interesting to see where this goes as it starts to move down that scale.
Is there any consideration for people with specific chronic conditions? I don't know if you had any of that data. I know you said the mortality data was kind of generalized, if you will. But you know, people with asthma, heart disease, etc. You know, I suppose you just kind of used rates now for the future. That seems to be the assumption. But any other thoughts on that?
I mean, in terms of, do you mean in terms of mortality or just in terms of health impact, period? I mean, because, I mean, in terms, I mean, you're right in terms of mortality. We basically said, I mean, everything was taken in the future, then we kind of had that overall knockdown value based on acclimatization, and it wasn't specific to condition or anything of that sort. Largely because we didn't really feel we had any sufficient knowledge to know how to do that with an appropriate value. In terms of morbidity, or in terms of like chronic issues, I mean, there are studies along those lines, but you know, one of the hardest things is that hospitalization data are a lot harder to work with than mortality data. And so, you know, seeing how many people come back if they have problems with asthma or something, or have chronic issues, there's a lot more, it's a lot more difficult to actually find those relationships, because people tend to have, you know, and this is going to sound crass, but you know, if you die, you die. You know, whereas if you go to the hospital, you typically have some choice in when you do this, unless it's incredibly acute. And so it tends to confound the weather relationship somewhat, because you know, people don't go on weekends, they go on weekdays, and a lot of other things. So we tend not to have this clear kind of relationship.
Just looking at the graph, it was moist tropical. I mean, it's quite interesting in the context of California, which tends to be quite dry in the south, and I mean, that's kind of the whole point. It's an entirely different type of climatic type. You know, can that be generalizable in a broader sense? You know, is it going to be moist tropical more generally as you move out? And I'm thinking of I'm an ecologist, so I'm thinking more like, you know, are we looking at major ecozone changes, or is this entirely more on a variability sense?
That's a really good question. My assumption would be, you know, if you kind of go back to the fundamental assumption that in a warmer world you're going to increase the hydrologic cycle, which means you're going to have more evaporation, which would mean collectively you'd have higher humidity. You'd expect on a broader scale that would probably be true. I think in this particular case, though, I think this is more just a function of the unique climate of Southern California. I haven't done this with any other region. I did a little bit of this with Chicago for one project that really didn't show anything like this. You know, and so I don't know if it's anything. You know, and again, a lot of this also kind of ties in ocean temperatures, which weren't explicitly put in here, but the climate models inherently had some of that in there. So I would give you, I would say a cautious yes, in a global sense, but on a local sense, I don't know.
So I have a methodological question. So if I understood it correctly, is dry tropical and moist tropical that you downscaled?
I'm sorry?
You downscaled the percentage of dry tropical and right? So what are their relationship with the 10 types that you mentioned in the beginning?
Okay. So the 10 types were basically the right. Well, that's all I don't have. Basically, the types can be each attributed to a certain likelihood of a weather type occurring at the surface. And the same with the upper level circulation patterns, and there's also a lag built in. So if you have a thermal ridge coming in one day, you might have a certain percentage likelihood of dry tropical, but if that thermal ridge stays over you for 4 or 5 days, then you have a much greater likelihood of dry tropical. So basically, these are just statistical relationships looking at the historical probability that these patterns and the sequence of these patterns would connect to a certain weather type occurring at the surface.
So you are taking the downscale data and you are creating these patterns, right?
These aren't downscale. These are the actual outputs from the downscale.
These 10 patterns.
Yeah, there is no downscaling. I mean, the only thing that you would want to call downscaling is the deriving the SSE type. See, that's I think I might. When we were talking at lunch, I might have. I think I skipped over that part. But basically, because we had issues with the downscaling, so we just got rid of statistical downscaling, and we just looked at the statistical connection between patterns and the weather type. And so that if you want to call that downscaling, that's a couple papers have called it synoptic downscaling.
So much simplified version, but very clear. Yeah, I see that.
Yeah, and then the other downside of it is that your end product then ends up being just a bunch of categorical variables, which makes the statistics a lot harder to analyze.
Yeah, I really enjoyed the last slide you see the contrast between inland and coastal weather station. You see how different SSC types are between the two zones. My question is pertaining to, especially for the location of Miramar. It's interesting how you mentioned August, where it's known as the hurricane season down in eastern Pacific, where it's the, I guess we call it the peak hurricane season. So I wonder how much that dramatic increase in moist tropical type would have to do with remnants or perhaps tropical storms from the eastern Pacific. I know maybe they don't hit the city of San Diego as often as Mexico, but the remnants can quite well track its way up towards Southern California. It's possible.
That's a good question. I always look at that, and I always look at the shape, and I just see the southwestern monsoon. Or if you look at Arizona, or like you look at Phoenix over, going towards Las Vegas, you see that plume of moisture coming up. And like if you look at the SSE cycle for Phoenix, it looks exactly like this. For July and August, it skyrockets. And so my first thought was that you could have a shift in the monsoon, streaming moisture up from the Gulf of California further west or the Pacific. But that's a good question about the tropical cyclones. I mean, one of the things we didn't do is we didn't actually look at what was going on aside from these patterns. So I don't know. You could probably analyze it and see what the likelihood is, but I don't know.